Hi there everyone, I'm Mayur Gohil. In this video lecture, we shall learn to find eigenvectors when eigenvalues are repeated. We have already seen in my previous video lecture how to find eigenvectors in the case when eigenvalues are distinct. So let us take an example. Consider this matrix A. Okay, now first of all observe that this matrix is a real matrix and it is symmetric. Okay, now the procedure to find eigenvectors is almost similar to that you have seen in finding eigenvectors when eigenvalues are distinct. There is a slight difference, so let us see. The starting is same. First thing is, let Ax is equals to lambda x, where x is not equal to 0. Then you move on finding the characteristic equation using determinant of a minus lambda I equals to 0, and in that case what you do is you write this matrix under determinant notation and subtract lambda from each of the diagonal values. Using the characteristic equation formula that I have already given you, you can find this characteristic equation, and this equation number 2 is the factor form of the characteristic equation. When I simplify it further, I obtain lambda is equal to 2, 2 and 5. Now what I see over here is 2 is repeated 2 times and 5 is repeated only once. So algebraic multiplicity of lambda 1 equal to 2 is 2, and that of lambda 2 equal to 5 is 1. Okay, now we have already cleared that algebraic multiplicity is a number of times an eigenvalue is repeated. So that is what I have written over here. Now let us go to find eigenvector for lambda 1 equal to 2. As we have seen that capital X, which is a column vector for us in this case, is x1, x2, x3 is our general eigenvector. In order to find eigenvector, what we use is, for lambda 1 equal to 2, we have Ax is equal to 2x. This 2 is nothing but your eigenvalue 2. Okay, and x is a non-zero eigenvector, that is what we are finding. Then on further simplification, we get the following linear system. That is, this is the coefficient matrix, and this is the matrix of unknowns that we are interested in finding, and this is the right hand side 0, 0 matrix. Okay, so now we have to solve this system of linear equation. We perform the row transformation. The following row transformation are performed, and what we obtain, we reduce the matrix to this system, and when we simplify it further, we obtain only one equation, that is x1 minus x2 plus x3 is equals to 0. If I further simplify this equation, I obtain x1 plus x3 is equals to x2. Okay, now observe that this system of linear equation that we have obtained, if we remember the concept of geometric multiplicity, the rank of this matrix is nothing but 1. Okay, and the number of unknowns or the order of the matrix is 3. So the geometric multiplicity of lambda 1 equal to 2 is nothing but n minus r, which is going to be 2. Okay, so n minus r is 3 minus 1 is equals to 2. So that is the geometric multiplicity of eigenvalue lambda 1 equal to 2. I would like to make a remark over here, which I am not mentioning here. If you remember, the algebraic multiplicity of eigenvalue lambda 1 in this case is also 2, and the geometric multiplicity is also 2. So you can note this small fact which will be used ahead for some another advanced concept. Okay, now carrying on the discussion further, we now try to find the eigenvector x. Capital X is nothing but x1, x2, x3, that's our general vector. We already found the relationship x1 plus x3 is equals to x2. So I plug up x2 as x1 plus x3. Now this vector that you see, I can write it in this manner, that is x1 plus 0 x3, and x1 plus x3 is the second component, and the third component can be written as 0 x1 plus x3. Further, I perform matrix addition rule, and what I can do is I can split up these two vectors, and I am pulling out the scalar out from the first vector, that is x1 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 vector over here, x1 x1 and 0 x1. I can pull out x1 outside, and from the second vector I can pull x3 out, okay, and leave the scalars in the matrix. So what I am left out is with 1 1 0, and in another vector is 0 1 1. So finally I obtain two eigenvectors, distinct eigenvectors for the same eigenvalue lambda lambda equal to 2. So now what I see is I have my first eigenvector x1 is equals to 1 1 0, and second eigenvector x2 is equals to 0 1 1. Okay, so this is the way you find eigenvalues when eigenvectors when a particular eigenvalue is repeated. Okay, now let us go ahead and solve for the last eigenvalue lambda 2 equal to 5. Now lambda 2 equal to 5 is a non-repeated eigenvalue, and it is repeated only once, so that is its algebraic multiplicity is 1. So the same procedure follows. Ax is equals to 5x, and then further when I reduce the system I obtain this as my linear system, okay, and on performing row operations I obtain following relationships. Now from the first relationship, that is minus x2 is equals to minus 3x2 is equals to minus 3x3 is equals to 0, I obtain minus x2 is equals to x3. And when I plug up this relationship in this particular equation, this equation boils down to x1 is equals to x3. Okay, now substituting the relationships that I have obtained in my general eigenvector, I see that the eigenvector gets converted to x3 minus x3 and x3. Pull out the constant, that is 1, and in the matrix I am left out is 1 minus 1 and 1. So substitute an arbitrary number for x3 but not 0. So x3 is equals to 1 I am putting, and I obtain my eigenvector x3 as 1 minus 1 and 1. So we are done. Now very important thing is that you have to understand the entire procedure properly, and then you can get your eigenvectors in a very easy manner. So this is the procedure, and same way try to find eigenvalues and eigenvectors for these three matrices. In each of the case you will be having repeated eigenvalues. These are your practice problems. So if you have any difficulties, please let me know. I shall be glad to help you on this concept. So till then, thank you.